Okay, want you to get your homework out from the last 2 days. Um, and I want to kind of jump around and pick some that I would like to talk about, and hopefully that will help you on the questions that you still have. Um, I want to start with looking at that 21, which I hope part of 21 isn't so bad, but I want to really talk about part D where it says describe the motion of the particle. So if you have your homework, if you can just get it out, if you can open your book to page 137 so you can see what it has here. Um, it says a particle moves along a line so that its position at any time greater than or equal to 0 is given by the function s of t equals t minus 2 squared times t minus 4. Did I make you do that one? Where s is measured in meters and t is measured in seconds. And part A says find the instantaneous velocity. And again, remember, you got to know what that's asking you, and it's asking you to find the derivative. Velocity is the derivative of the position function. But before you can find the derivative on this, you got to multiply this out. We can't do the product rule right now with this t minus 2 squared. I guess if you wrote it as t minus 2 and t minus 2 and t minus 4, you could do the product rule with the three functions if you wanted to. But I just worked it out. So if I FOIL this out, then I'm going to get t squared minus 4t plus 4. And then you got to distribute again. And I'm just going to go ahead and tell you what my answer was. I hope that you did this. I got t cubed minus 8t squared when I combine like terms plus 20t minus 16. And that's just working that out so that I can take the derivative without having to do a whole lot of crazy rules here. So for part A, when it says find the instantaneous velocity, I'm just going to take the derivative here and get 3t squared minus 16t plus 20. And then part B says find the acceleration at any time t. And remember that the acceleration function is the second derivative of the position function, or it's the derivative of the velocity function, which means I'm just going to take the derivative of this of part A and get 6t minus 16. And then part C says when is the particle at rest? And again, think about what the velocity is if it's at rest. If it's at rest, it's not moving, which means the velocity is 0. So instead of asking now to find horizontal tangent lines, or where it would have a horizontal tangent line, which we knew we would set the derivative equal to 0, now we're going to set the velocity, which is a derivative equal to 0, because it's asking us to find when it's at rest. So I'm going to set 3t squared minus 16t plus 20 equal to 0. And that's a quadratic. You could do the quadratic formula here. I don't really know that completing the square is the best option. But it actually turns out that it's factorable. You can multiply 3 times 20 together and get 60 and figure out what multiplies to give me 60, that subtracts to give me 16, no, adds to give me 16. And I think that's going to be 6 and 10, because negative 6 times negative 10 is 60, and negative 6 plus negative 10 is negative 16. So do my lovely factor by grouping. Oh, that should be a 3t there. 3t minus 10. So I get at 2 seconds and at 10 seconds, or 2 and 1/3 seconds, is when the particle is at rest. And then part D, I really did this one because I hope parts A, B, and C are not that bad. I know a lot of these had lots of parts on them, but a lot of them were just finding derivatives, setting derivatives equal to 0, setting acceleration equal to 0. But part D says describe the motion, and I know it's odd, and I recommend that on these odd problems you check the back of the book, especially on ones that are talking about writing, because that's kind of the new part for us in math class. But what I want you to think about is, based on what we know and maybe a couple more things, we can kind of describe what's happening to this particle. And one way you can figure out what's happening is to look to see when is the velocity positive and when is it negative. Because if this is moving across the line, when the velocity is positive, that means the particle is moving forward. And when velocity is negative, that means it's moving backwards. An easy way to tell that is to look at the graph of the velocity. So if you have your graphing calculator, which I'm going to see if I can pull up here really quickly. Hopefully this still records while I do this. Graphing calculator. If I graph that velocity function, which was 3t squared minus 16t plus 20. I'm just going to change those to x's. 3x squared minus 16x plus 20. And I'm going to change my window to start at x equals 0. And I'm just going to go to like 10. And I don't really know that I need to go higher with my y's. I'm just going to go ahead and hit graph. But I'm starting at x equals 0 because they tell me that time greater than 0. And remember that I'm graphing the velocity here. I already know that velocity equals 0 twice, right here at 2 seconds, and this is at 10 thirds. I guess I said that was 2 1/3. I think I meant 3 1/3. And what I would say for part D is one more thing before I start writing here, is because we start at time equals 0, let's figure out the position. So I would start by saying at time equals 0, the particle position is, and I don't know what the particle's position is, but I could go back here and I could go up to the position function and I could just plug 0 into this function, because this is position, and if I plug 0 in for time, very easily I can see that it starts at negative 16. All right, is that really required? Maybe not, but it's not a bad place to start on these, and I think that the book always says this. So I'm going to say the particle's position is negative 16, and it's moving when it starts. I know I don't have negative 16. I don't have the velocity when it starts because it's not on my graph here. But I can see that the velocity is positive. So if my velocity is positive, I know that it's moving in a positive direction, which means if we're talking about moving across the line, I know that it's moving forward. So I'm going to say it's moving in, or sorry, I'm going to say it's moving forward. Why is this not working? Forward. Until when? When does it stop? Right here, at 2 seconds. Until time equals 2 seconds, when it changes direction and is moving left. How do I know it's moving left? Because the velocity is negative. And when the velocity is negative, I know it's like moving backwards. So I guess I could say moving back. I don't know why I said left there, but I was just thinking forward and back. And it's moving left until when? Until the next time that it has a turning point. So it's moving left until time equals 10 third seconds, when it starts moving forward again. Well, that's lovely. When it starts moving forward. And you can look in the back of the book and you can see how they write these. And I just want you to start thinking about them. If I asked you to describe the direction, if you could do that. And so I just wanted to make sure that I addressed that, because I think there were a couple on there. On my paper I wrote starts at t equals 0 s equals negative 16 and moves right until time equals 2, then moves left until time equals 10/3, and then continues right because it doesn't ever change direction again. And I can tell all that from that graph, okay? Another one I wanted to address really quickly, maybe not the whole thing, but number 38 gives you this lovely picture of a multi-flash photograph showing two balls falling from rest. The vertical rulers are marked in centimeters. Use the equation S equals 490 t squared, the free fall occasions for S in centimeters and t in seconds, to answer the following questions. I'm not going to write all this on the board, but just to kind of work you through it, it says, how long did it take the balls to fall the first 160 centimeters? They give us the position function, which means they want to know what was the time when the position, or S, was 160. So I think for part A, you should just set 160 equal to 490 t squared. And I left mine as a fraction because it's more exact, but you could round to a decimal. Oh my goodness. And when I solved this, I threw out the negative answer, and I'm just going to tell you, I got 4/7 of a second. And it says, what was their average velocity? So remember that derivative is instantaneous velocity. So when it says average velocity, please don't do the derivative, right? Because average velocity is just the distance divided by the time. And so you can just do the average velocity. How far did it fall? 160 feet. And how long did it take? 4/7 of a second. So to find the average velocity, actually I think it's centimeters, sorry, that's a long way for a ball to fall. You can work that out and get the average velocity that ball was moving. Now when it says how fast were they falling when they reached 160 centimeter mark, what was their acceleration then? That's when we're going to do the derivative and then the derivative again, because velocity and acceleration is what we're looking for there, and we're looking for the time of that. So you're just going to plug that 4/7 in there. Part C, I really want to talk about this because I helped someone with Part C yesterday, and I was like, oh, I guess I should mention that this really doesn't have nothing to do with calculus on Part C. So Part C says about how fast was the light flashing, flashes per second. So it's kind of hard to tell from there, but I'm pretty sure this picture shows the 160 centimeters, because if you count on there, there's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, 30, 40, 50, 60. Like the last ball stops at 160 centimeters, which would be nice if they told you that, but they just expect that you're going to look at the picture and figure that out. And so they're asking you to find how many flashes per second. Well, we already know that it took 4/7 of a second for this to happen. And think about every time it takes a picture, there's going to be a picture of a ball there. So if you go through and you count, not counting the very first one because that's the actual ball, if you count how many flashes there were, I counted 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I just did it again. You just take that there were 16 flashes, and it took 4/7 seconds for that to happen, and then you can get how many flashes per second. Again, some silly stuff there, but I just wanted to help you on some more from 3-3, or whatever section this is, 3-4 day 1. I do want to look at one, maybe a little bit of one. How much time have I used here? 15 minutes. Okay. From yesterday, 27. Again, just going through some words here. The vocabulary is so important. On 27, part A, it says average cost. Average cost has nothing to do with the derivative. Average of something, you're going to add it all up and divide by the number. Well, we can find the cost. The cost of 100 is just C of 100. You plug 100 in there. That's the cost of 100 washing machines. But to find the average cost, you're going to take that divided by how many you're doing there. So average cost, you should be doing. Marginal cost. You have to know when you see the word marginal cost, you mean derivative. So for part B, you should just do C prime of 100. And then part C is the part that Philip kind of got to yesterday. He kind of told us the answer to this. It says, show that the marginal cost when 100 washing machines are produced is approximately the cost of producing one more washing machine after the first 100 have been made by calculating the latter cost directly. That means they want you to do the cost of making 101 washing machines, right? But we don't want the cost of all 101. We just want that one. So you subtract out the cost of 100. Nothing to do with the derivative. That's what it means by calculate it directly. And you should get it pretty close. Like I got 80 for part B and $79.90 for part C. And then I also gave you 28, and it says draw the graph of R. There's no expectation that you draw that by hand. Use your calculator. Change the window so that you can see the whole graph. And when I graphed that, I got a graph that looks sort of something like that. And I made my x-axis go from 0 to 50. And I made my y-axis go from negative 500 to 2200. Just so I could kind of see what was happening there. But it says, what values of x make sense? X is a number of custom-made office desks. Well, definitely we couldn't make a negative number of desks, so you should say that, it has to be greater than 0. If they're custom-made office desks, I don't know how many people you have working for them, but what's a reasonable amount? And I just made my graph go from 0 to 50 because am I really going to make more than 50 custom-made desks in a week? I think that's probably not going to happen. Part B says find the marginal revenue. I just wanted to point out I helped a few people with this yesterday, and they all made the same mistake. When you find the derivative of this, you cannot just forget about that 2,000. You have to either do the product rule or you have to distribute. If you do the product rule, you also have to do the quotient rule when you get over there to that x plus 1 that's in the denominator. So I just distributed. And I'm not going to work this out for you because I want you to do it. But when I distribute, I get this. And now you're right. The derivative of 2,000 is 0, but it's not a product anymore. So now you can just do the quotient rule with the second half, and you can get the marginal revenue. We're talking about revenue here. It should not be a negative number. So if you got a negative as your derivative, I'm guessing you had a negative issue when you were doing that. And then part C says use the function to estimate the increase in revenue that will result from increasing sales from 5 desks a week to 6 desks a week. Which means you don't have to plug in 5 and plug in 6. When it says use R prime of X, remember that represents the marginal revenue. Marginal means the very next one. So if I want to see like how much more am I going to make if I go from 5 to 6, I'm just going to plug 5 in there because that's going to give me like the cost, or in this case, the revenue that I would get from that 6th desk. Part D says find the limit of R prime of X as X goes to infinity. How would you interpret this number? Oh my gosh, they're talking about limits again. They're talking about limits going to infinity. You can use the rules with the exponents on that, and I think that we would get You can look at your own, but I got 0 as my limit. Of r prime of x. And if we're talking about revenue, think about what that means. And again, I think Philip kind of talked about that yesterday. I don't know if you guys all heard it or not. But look at your graph here. If this is my revenue, at some point, I'm really not going to be making any more money. There's a point where you're making like the maximum revenue, but you make so many desks, you're really not going to make anything off of that. And so that's just, writing to learn there. All right, last ones I'm going to talk about is 49, and I'm not going to spend a whole lot about it. The back of the book, if you looked at it, it did a whole lot of proof using the definition of a limit, because an even function, if you plug in negative x, you get back the same thing as if you plugged in x. An odd function, you get back the exact opposite. I just wanted you to think about it. Use some examples. If you pick an even function like x squared, when you take the derivative, it's going to be an odd function because it's going to be 1 degree less. And if you pick like x cubed, which is my favorite odd function, it's going to be 2x squared. Who was it? Jake Berg was talking about sine and cosine, which we haven't really learned those yet, but that sine is odd and cosine is even, and they're sort of each other's derivatives. We haven't quite got there yet, and it's not exactly true. But you don't have to actually prove 49. And 50, I gave you the rule for 3 derivatives, or 3 functions. If you wrote it down in section 3.3, I gave you that. So hopefully you're getting this somewhat filled out. What I have for you today is a little homework quiz over 3.3, and maybe there's like one question from 3.4 that if you've made an attempt at 3.4, it should be one that you got answered. And so when I'm done talking here, you guys need to spread out like you normally spread out to take your homework quiz, and you're going to get a homework quiz to do. And then you're also going to get a worksheet when you get done with that. That worksheet isn't due until Monday. So if you aren't taking the AccuPlacer tomorrow, then you can work on that worksheet tomorrow during class. If you are taking the AccuPlacer tomorrow during class, then you can work on it tonight. You can work on it this weekend. It's only an 8-question worksheet, which means it shouldn't sway you one way or the other whether you're going to try to take the AccuPlacer. Tomorrow, first thing, there'll be a sub again, but you need to get a computer. You need to get logged in, and I've left directions to get on for AccuPlacer. Jake Berg has done this before, so he can be helpful, and Mr. Pruitt is going to be down here to help as well. And again, if you don't get finished, remember you can save where you are. But I'm going to quit talking so you can do your homework quiz, and I will see you guys on Monday.